Now let's look at a more modern view and understanding of atoms. After Thomson and Millikan, with their successful experiments, there were lots of other scientists who tried to understand the nature of electrons and the atom. One of the most famous of these is Ernest Rutherford, just shortly after Millikan's great experiment. What he did was he took alpha particles, which are radioactive particles that are emitted from radioactive elements, and he took these alpha particles and he shot them at a piece of gold. So here in this figure you can see a lead container with a radioactive source in the middle, and then the radioactive material would emit these alpha particles, and it would be directed directly at the sheet of gold. Now, he surrounded this gold with a piece of foil that was used to detect the impacts with alpha particles. So if the alpha particles hit it, it would glow and you would be able to see where it was hitting. Now, Rutherford had a number of ideas of what might happen, but the result was actually quite startling. Remember that we have the plum pudding model of the atom, which is that you have a solid ball of positive charge with negative charges embedded inside of the positive ball. So it should have been a rather positive, sorry, not positive. It should have been a rather solid material, very difficult for the alpha particles to pass through. But the result was that most of the alpha particles actually passed through without bending much at all. There were a few that were scattered at large angles, some in front, some behind, but most of them passed through without even being touched. So the conclusion was that these alpha particles, most of them passing straight through the atom, meant that the atom had to be made up mostly of space, of nothing, a void. And so the positive charge of an atom was rather a massively positive charge at the very, very center of the atom, and then a bunch of space around that, and then the electrons orbiting the nucleus. A rather startling and awesome result, which we have discovered to be true. Later on, they defined these positive charges to be protons, or the positive particles inside of a nucleus. So at that point, it was thought that a nucleus was made of protons, and then electrons would just orbit that. Later on, 1932, James Chadwick also found out that there were other particles inside the nucleus, neutrally charged particles, which we now call neutrons. Now that we know what an atom is made of, let's talk a little bit more about how we identify one atom from another, from different elements. The basic principle that we use is the atomic number. The atomic number indicates the number of protons in a nucleus. Now, this number of protons determines and distinguishes one element from another. So hydrogen, for instance, is an atom with one proton. Helium would be an atom with two protons. Lithium, an atom with three protons, and so on. There are 113 different elements that are identified. In other words, there are elements 1 through 113, each with that particular number of protons. Now, to have an atom neutrally charged, then that means that the number of positive charges, or protons, has to equal the number of negative charges, or electrons. So to have a neutral atom, that has to be the case. Protons equals number of protons equals the number of electrons. However, that says nothing about the number of neutrons. So you can have two different atoms that have the same number of protons, so they're the same element, but they can have a different number of neutrons. For example, let's take a simple hydrogen atom. You have hydrogen 1, which would be a proton, positively charged, and an electron, negatively charged, orbiting around the proton. Now, we would indicate that by saying it's hydrogen, the letter H, 1 meaning there is one proton. This would be your atomic number. And the upper number is what we call the mass number. The mass number is protons plus neutrons. Since there's only one proton, then that total is 1 in this case. Now, there is an isotope of hydrogen where you have not just a proton, but also a neutron, and then an electron orbiting that. Now, the positive and negative charge of hydrogen 2, charge still balances out to 0, so it is still neutrally charged. There's still only one proton, so it is still hydrogen, since there's only one proton. But now there are two elements in the nucleus, one proton, one neutron, so the atomic number is now 2, so this is hydrogen 2, also known as deuterium. Tritium would be one proton plus 2 neutrons, so that there are 3 particles in the nucleus, one proton plus 2 neutrons, giving you a mass number of 3. In all of these, the atomic number is still the same, 1. Because there's one proton, that makes it the same element. It's all hydrogen. But the differing number of neutrons changes the mass number, thus changes a little bit of the properties of that particular hydrogen atom. So mass number is number of protons plus neutrons. But strangely enough, one proton in one atom may not have the same mass as a proton in another atom. This has a lot to do with the density of the nucleus and the number of neutrons, so on. There's a lot that comes into it. Basic point of that is that we take the atomic mass unit to be the mass of a proton in perhaps one of the most fundamental elements of life, and that is carbon. So you take a carbon-12 atom. Carbon is element number 6 on the periodic table. So it has 6 protons. So carbon-12 has 6 protons and 6 neutrons. And we divide that 12 into by 12. So we get the average mass of each particle. That is one atomic mass unit. For example, here in this table below, we have nitrogen 14, which means you have 7 protons and 7 neutrons. Its total mass would be 7 plus 7, or 14, but you can see that the actual weight is a little more than 14 atomic mass units, because the average mass of protons and neutrons are a little bit more than in a carbon-12 atom. Now, when you look at a periodic table, you can read the atomic weight of these atoms. It's important to note that these atomic weights are averages of all the isotopes. For example, nitrogen, we looked at nitrogen 14 here in this table. About 99.63% of the nitrogen that we encounter is nitrogen 14. But there is still 0.37% of that nitrogen is actually nitrogen 15, meaning 7 protons still, because it's still nitrogen, plus 8 neutrons to give you a total mass of 15. Now, if we take those two and make an equal average, meaning 99% of them have a mass of 14, 0.37% of them have a mass of 15, average out all of those together, then you get a total average of 14.0067. So that is an important point to note. When you look at the atomic weight on a periodic table, you're looking at the average weight of all the isotopes. Now let's get into the quantum concept of chemistry. This is has its roots in physics, but is the basis of what the atom really is. This started with Max Planck in the year 1900. He introduced the idea that energy is quantized, meaning you can have certain amounts of energy, but the amounts of energy in between those two amounts does not exist. It does not happen. So that was the theory. A lot of people laughed at that, said that's ridiculous. But then a few years later, Albert Einstein came up. Right around the same time he came up with his theory of relativity, got into this idea of quantized energy, and proved that light is made up of quantized packages of energy, certain amounts of energy, with no energy in between those two amounts. These packages of energy we call photons. And the higher the frequency of the photons, the more energetic the photons are. And he introduced, both Planck and Einstein, through their theories, came up with this equation, that the energy of a photon is going to be the product of the photon's frequency and a number which we call Planck's constant, 6.63 times 10 to the minus 34th joules times seconds. So let's take a look at a photon of red light. Red light has a frequency of 450 terahertz, or 450 times 10 to the 12th hertz. That would mean that one wave of red light has a wavelength of about 700 nanometers. A very, very small wavelength. So the amount of energy inside of this one photon we can calculate as the product of Planck's constant times the frequency. 6.63 times 10 to the minus 34th joules times seconds times the frequency, 450 times 10 to the 12th hertz. This gives us a product of 2.98 times 10 to the minus 19th joules. So that is the amount of energy in one wave of, or in one photon of red light at that frequency. Another series of studies at the same time as Max Planck was focused on what we call black body radiation. That is the continuous radiation emitted by objects that are emitting light. Now, what we found is that if we take the light from some light source, send it through a prism, the individual colors will spread apart, and you get yourself a rainbow effect, very much like what we saw back in our optics chapter. What else we saw with this black body radiation study is that sometimes one color was more intense than another. The most intense color depended on the temperature of the radiating object. It was a characteristic of whatever it was that was emitting the light. It was a characteristic of the different solids, liquids, and dense gases. Now, when we do the same for other materials that are emitting light, we find that it doesn't necessarily create a full rainbow effect like we saw with the black body radiation. If you have, say, hydrogen that you cause to excite and emit light, and we'll show you how to in just a couple slides, then it will emit light, but it only emits a few colors, 3 or 4 colors of light that we can actually see. And so certain elements will emit light, but the colors of light are characteristic frequencies of the element itself. So this led to a whole new series of studies. And one of the key players in this study was Niels Bohr. Niels Bohr looked at a new way of how the atom works. He said that electrons can exist in more than one orbit. It's not just a nucleus, and then all your electrons in one orbit, you can have multiple different types of orbits. Now, Niels Bohr ruled that he found out that electrons can only exist in certain orbits. So in this picture, you have an electron that can exist in a lower orbit or a higher orbit, but it will not exist between those two orbits. So it can only be one orbit or the other. It will not ever be anywhere in between. He also found that an electron, as long as it's sitting in one orbit, so say you have an electron in the higher orbit, as long as it stays in that higher orbit, it will not radiate anything. It does nothing except orbit the nucleus. But if that electron jumps from the higher orbit down to the lower orbit, then it will emit radiation or a photon. So the electron drops down from one energy level to another. So there is a certain amount of energy that the electron loses. The energy of this photon is going to be the same amount of energy. Remember our law of conservation of energy? Energy is neither lost nor destroyed, only changed from one form to another. So here, the electron loses energy, but that same amount of energy is released in the form of a photon, which of course we can calculate as Planck's constant times the frequency. Now, another thing can happen here. If I have a photon coming in and it hits an electron in the lower orbit, the electron can also absorb that energy and jump up to the higher orbit. So electrons absorb photons and then jump to higher orbits, or they jump to lower orbits, releasing or emitting photons. The lowest possible energy around a nucleus is what we call the ground state. Any energy level above the ground state, we call that an excited state. And the amount of energy in a photon is going to be equal to, as we said in the previous slide, the difference between the two states of energy from which through which the electron jumps. So here we've got a figure showing 6 different energy levels. Here, level 1 is always considered to be the ground state. So this is the lowest possible energy level. And 2 through 6, these are your excited states. And so electrons can jump from any of these excited states down to lower excited states, and as they do so, they emit photons. Now, there are a particular series in a hydrogen atom called the Balmer series, or the Balmer lines, where if you have electrons jumping from the 3rd, 4th, 5th, or 6th energy levels down to the 2nd energy level, that will emit a photon of either red, blue, violet, or a different shade of violet. You can see all 4 of those colors if you look at the light of a hydrogen atom that a hydrogen atom emits. Now, these numbers indicated on this figure, these are numbers that are unique to hydrogen. So the energy of a photon is going to be HF, but we can find that as, say, the energy of your higher level. So say we jump from the 5th state down to the energy of the 2nd state. So we're jumping from the 5th down to the 2nd. Now, the 5th level, we see that as a negative 0.544 minus E2, which is a negative 3.40. Let me quickly calculate that. That gives us, oh, let me try one more time. Hang just a second. That gives us a total of 2.856 units. Here are electron volts. And that's it's another unit similar to the joule. And that is how much energy is in the photon emitted, namely violet light. So Bohr's theory, the numbers that you saw in the previous figure, based on Bohr's theory, only modeled the line spectrum of hydrogen. There are a whole lot of other gases and elements that react very similarly. There are lots of other experiments similar to this as well that show the duality of light and matter. In other words, light and matter have a tendency to act both like waves and particles. For instance, recall from the optics chapter, Young's two-slit experiment, where light shines through two slits and it produces a rainbow pattern, an interference pattern. That was looking at it with light or photons. But what we discovered is that the same thing happens when we use electrons, matter. So it turns out that light and matter both have this wave-particle duality.